Hello, I am Samuel Mesele. I'm a soil scientist and I work with the International Institute of Tropical Agriculture. And I welcome you again to this important event, another interesting episode of the showcase event of the Community of Practice on Soil Information being led by ISRIC based in the Netherlands. And today we are going to have a wonderful time. As I've said earlier, I'm Samuel Mesele, and I'm the subcommittee leader on data collection. Today we are having a very interesting topic that look at soil pollution and remediation, and I have the honor to introduce to you Dr. Albert Kobina Mensah, who is going to be our lecturer, so to say, who is going to take us through the concept of soil pollution and remediation from a practical perspective in Ghana. He works with, he's a researcher at the Soil Research Institute, CSR, in Ghana. Dr. Mensah, you are welcome, and you can take the floor.
Thank you so much. I'm humbled and pleased to be here this afternoon to give us sort of a joint discussion on my new book that has been released, and it was published by the Greta on the 19th of May 2025. So that is basically what I'm going to talk about, and I'll present my work, and after that we can have a discussion. Permit me to begin by saying that even though we are professionals in the area, but we do not claim to know it all. But at least we know quite a number of stuff and our way out as far as soil pollution and remediation is concerned. So I will first start the lecture with a brief background about myself. Then we'll talk about risk assessment. Then we'll talk about solution to the problem. So first of all, I'll introduce myself. Then now we can move on with the other agenda on the table. So first of all, I work with the Soil Research Institute in Ghana, and I also belong to the DAD Scholars Association, both in Kenya and in Ghana. And I also belong to the Soil Science Society of Ghana and the Research Staff Association of the CSIR here in Ghana. I had my Ph.D. in Bochum, Royal University, and I also am capable of speaking German to a very limited extent. I have my master's from Kenyatta University in Nairobi, and I did my Bachelor of Science degree also from the University of Cape Coast. I began my secondary school here in Ghana, and also my basic school also was in Ghana. So I've had quite a number of awards, including the German Academic Exchange Service, the DAD scholarship for Ph.D. training in Bochum, Germany. And I also had a DAD scholarship for my master's program in Nairobi. In my former secondary school where I graduated in 2004, I was the best graduating student in that year. I also have quite a number of teaching and research professional experiences. I was a postdoctoral fellow from the Royal University Bochum in Germany. I also did my Ph.D. in the same department. I taught as a teaching assistant for a course on environmental protection and mining. Then I also teach as a lecturer in the CSIR College of Science and Technology in statistics and research methods. I also teach at the University of Cape Coast on part-time in problem soils. Some of my professional experience, I've had some research stay from the University of Cape Coast in 2017. When I got back from Kenya after my master's, I taught at secondary school here in Ghana from 2012 to 2013. 2012 to 2013. Then I also, in Ghana, there's something called national service. where after university, you are supposed to serve your country for 1 year. I did it as a teaching assistant at the University of Cape Coast at the Department of Soil Science. Then I've also worked with a number of environmental organizations here in Ghana. These are some of the projects that I've conducted. These are some of the peer review publications that I've done. This is just a selected few of them among them. Then these are some published abstracts. Then some published books that I've done. Then my PhD was on arsenic contamination from gold mining and remediation of active and abandoned gold mining spoils in Ghana. And I defended it on the 21st of December 2021. It consists of 6 chapters. It includes 6 published papers, and it's made up of 232 pages. So let's now start what the book is about: soil pollution and remediation. First of all, we have in Ghana, which actually forms as part of the top 10 countries in Africa, usually at the first or the second position as the leading gold. So Ghana forms part of the top countries in the world where gold production is done. And also in Africa, we are usually the #1 or the #2 position, especially competing with South Africa. Gold contributes to the economy in terms of employment, in terms of livelihood creation, in terms of solving creation of corporate social responsibilities in mining communities. Nevertheless, the sector has also caused numerous environmental consequences, especially with regards to the artisanal small-scale mining here in Ghana. So first of all, these are the processes in the gold extraction. We find the gold is, I'll use the pointer. So the gold is actually extracted from underground, the rock. Then the rock is sent to the processing plant through this haulage. Then it is done at #4, which is the processing plant. Then the waste is stored as stockpile, which is known as tailing. Now, when it rains, these tailings, toxic elements over here are mobilized into water bodies around, and also it can also become airborne. So, especially in Ghana, small-scale mining has caused numerous environmental consequences. This is a typical example of a small-scale mining activity where their waste are indiscriminately stockpiled without any protection. So we can see over there how the waste has been stockpiled, and it has been created in the form of a mountain. Now, when it rains, all these are capable of getting into the environment and also into the ecosystem. So we have another one on our left, on our right, where water slurry from the gold mining site is released into the environment with no protection against environmental health. Then we also have children who use some of this abandoned mining site as playground. I captured this picture when I was doing my PhD from one of the sites where I was working. So we find children here, and this area contains arsenic of almost 8 grams per kilogram. And these children are using the site as a playground. And you know, when you leave abandoned mine site also unreclaimed, and when you do not take measures against responsible mining, some of these toxic elements that are released into the environment can get into our food chain. And we know we love our rice so much. It can get into rice, especially with cadmium and arsenic. Then we can also have some problem with skin diseases. When you go to Bangladesh, the major problem in Bangladesh over there is arsenic pollution, where arsenic has caused numerous health impact in the communities in Bangladesh. The problem there is usually with arsenic pollution in their groundwater. So, for instance, this actually represents the countries in the world that are affected by arsenic pollution. It's not only arsenic, but even when it comes to other toxic elements like cadmium, lead, and mercury, Ghana is actually a part of the countries that are highly polluted, or the environment is highly polluted with arsenic. So we are supposed to take measures to sort of to measure the risk and to be able to see the impact that it is going to have on our ecosystem and also on our health, as well as also on the on health of animals. So first of all, over here, I'm going to take you through various measures with which we can measure soil human health risk. It's supposed to be determined, and we can also estimate the human health risk from this particular problem. The first thing we do is to take a measurement of the total element content. That is the first thing we do to identify potential toxicity of an element, which has been specified in my book, where I talk about the various methods for identifying human health risk associated with exposure to contaminated soil. So we can do that through aqua regia or nitric acid digestion. But when you do the total element, it's not a true measure of toxicity. It can also overestimate or it can underestimate the toxicity. Then the other way we can also measure risk as far as soil contamination is concerned is to use contamination factor, use enrichment factor, pollution load index, geoaccumulation index. Then we can also estimate the risk with using hazard quotient and hazard index. We can estimate the carcinogenic and non-carcinogenic health risk through inhalation, through dermal contact, and through ingestion. Now, there's also another method for determining risk associated with contaminated soils. And one of the methods is to use sequential extraction. Now, sequential extraction separates the PTE or the potential toxic element to different binding forms or to chemical fractions. It is because we believe that the total element fraction is not able to, it's not all the total element, it's not all the elements in the total fraction that become available for pollution. So because of that, we are supposed to devise a strategy where we can measure those ones that are mainly of environmental concern. So you go through 8 steps. Some of them also go through 5 steps of extraction, where you use the same soil, you extract the non-specific sub-fraction or the water-soluble fraction, which is the most challenging associated with environmental risk. Then we can also extract the exchangeable part, which is the fraction 2, which is the part that can be exchanged with the food chain. Then you can also extract the crystalline iron oxide fraction, which is usually very small. Then we also have the amorphous iron oxide fraction, which usually is bound to iron. Then we also have manganese or even aluminium. Then we have the residual fraction, which is the fraction 5. So in my book, I detailed all these ones, and I gave explanations as to how we can determine all these ones. So for instance, we have this particular soil over here, and the soil was divided into 5 fractions, from fraction 1, fraction 2, fraction 3, fraction 4, and fraction 5. We saw that the main problem has to do with the fraction 3 and the fraction 5. Now, when we have a lot of arsenic in the fraction 3, it tells that it is potentially mobile. It means that the area can become highly polluted with the toxic element, because the arsenic or the PTE is bound in such a way that it is in the amorphous component. And amorphous component means that it is able to form 2 things, what is called the inner sphere complexes and the outer sphere complexes. So that makes the PTE content or the heavy metals in this fraction very high. Then the other one is the residual fraction, which is the fraction 5. The fraction over here means that it is not made available for pollution. So what we do is that from fraction 1 and fraction 2, it is called the mobile fraction. Then fraction 1 to fraction 5, or sorry, fraction 4, is called the potential mobile fraction, which we have given how to use this to estimate the risk associated with heavy metals in the soil. Then fraction 5 is the unavailable fraction, especially when you leave the land over there for a very long period of time. Most of the soil, through the processes of what's called pedogenesis, shift the toxic element into forms that become unavailable. Then you can also do what is called size fractionation. Size fractionation, what we do is that you separate the soil into size fractions, clay, silt, and sand. Then you can determine the heavy metal, whether it is bounded it is actually concentrated in the clay, in the silt, or in the sand. You know, that one gives us a true picture about the toxicity of the problem. And the advantage and the strength of my book is that it details how to do this method of sequentially separating the soil into size fractions, and not just determining the total content where we just use the whole soil. So you separate the soil into different size fractions. Now the clay and the silt can be called fine fractions. Then the sand is called coarse fraction. Then you determine the heavy metals in these various soil separate. Usually you will find that soils with higher clay content contain greater portions of PTEs than sandy soils. There's also high potential mobility in the fine fraction, and there's also release of the soil PTE under changing environmental conditions, especially those ones that are potentially mobile, especially from fraction 1 and fraction 4. From fraction 1 to fraction 4, they are potentially mobile, meaning that at every condition or at any enabling environment, those fractions that have been sequestered can also be released for environmental pollution. So this is one of the examples that I gave. So where the soil is separated into silt, clay, and sand. Then the silt and the clay are fine fraction. Then the sand is the coarse fraction. We saw that greater proportion of the soil of the arsenic or the PTE are normally contained in the what is called the fraction 3, which I explained as the fraction where it forms inner sphere and outer sphere complexes. Because of that, the fractions are usually higher. Then the residual fractions are also usually higher, meaning that the area is actually polluted or contaminated by true geology or through the parent material at the place. Then the other thing you can do is to use redox chemistry. In redox chemistry, all what you do is we have this example where we use redox microcosm experiment. In redox microcosm experiment, you fill the soil, you have a jar. So this jar, you feed them with soil, 200 grams, which is air dry. Then you add a ratio of 1:8. So here you multiply the 200 grams by 8 so that you can get the tap water that should be added. When you finish, you add glucose. Then the glucose, you cause it to constantly stir. Then you sort of introduce nitrogen to cause reduction condition, and we introduce oxygen to also cause oxidation condition. Then you use the syringe periodically to fetch the slurry from this. Then when you use the syringe to fetch the slurry from this, then you do the separation or everything, the filtration and everything, you do it in something called glove box. By separating the dissolved fraction, which is through a filter paper of 0.45 micrometers, 0.45 micrometers. Then now when you do that, after that, the separation is done in the glove box because you don't want anything to interfere with oxygen. But coming into contact with oxygen can actually affect the reading. So you do everything in that particular glove box for accurate results. So you get some, at the end of the day, you get your separated or the filtrate, which are ready. Then you determine the toxic element, especially arsenic on it, or then you can determine DOC, anything you want to determine, anions, specific ultraviolet absorption. I mean, you can determine all these things, provided you are of the view and of the theoretical background that these particular parameters have the capacity to influence the toxicity or influence the mobilization of this toxic element, like iron, like aluminum, like manganese, sulfur. We have DOC, dissolved organic carbon, anions, and silver. All of them can influence and have a bearing consequences on the mobilization of the toxic element. So that is why you just don't have to measure the toxic element, but you also have to measure those parameters that are connected with the influencing the mobility of that particular element. Then we also have pH. pH. So pH is also one of the major elements or one of the major factors that that can influence mobility of toxic element. Now, pH influence mobility of toxic element through two main ways. Lower pH result in higher mobility and availability of cationic species. Oh, HOD. Sorry, there was some interference. Sorry. So over here is pH. pH is argued to be one of the major factors that can influence mobility or toxicity of toxic element, especially through two main ways. When the pH is low, it results in higher mobility and availability for cationic PTEs. Then when the pH is also high, it results in higher mobility of especially anionic PTEs like arsenic. So over here, there's an experiment you can do, which is called a acid neutralization capacity experiment. What you do is that you introduce different amount of toxic element, especially different amount of acid and bases to the soil. Then when you add different amount of, let's say, bases to the soil, you sort of increase the pH. Then when you add different concentrations of acid to the soil, like hydrochloric acid, you tend to reduce the pH. So what you do is that after you have added different amount of acid and different amount of bases, then you in the filtrate, you measure the toxic element in the filtrate, or what is called a heavy metal in the filtrate. So for instance, over here, I added different concentrations of hydrochloric acid and different concentrations of potassium hydroxide. Now, when you add different concentrations of hydrochloric acid hydrochloric acid, you find the pH fell from 0 to 10 concentration, or from 0 to 10 molar of the solution. Then we also have from 0 to 5 molar of the concentration through addition of potassium hydroxide. Now, when you measure the arsenic in it, you can see that the arsenic over here, the concentration of the arsenic mobility will fall. That's what you can see here. It reduced. Then as the pH went up, arsenic mobility also went up. It is because at higher pH, there's deprotonation, and the deprotonation will introduce more of negative charges, and negative charges coming into the solution will facilitate the mobilization of anionic PTE, which arsenic happens to be one of them. But we can see that when you come here, the opposite to be found when you are dealing with like lead, or you are dealing with cadmium. Now, over here, when you are dealing with cadmium, you realize that when the pH gets low, the mobility of cadmium will also get will become more of concern. Then when the cadmium when the pH goes up, the cadmium mobility will reduce. So that's what we're going to see. Then there are also other techniques like synchrotron radiation science. There are other ones you can use spatial distribution of PTEs using GIS. You can also use incubation studies to see the problem or to identify the risk. You can also use spot experiments to also talk about to identify the risk. Then that is the first part of the book. The second part of the book now talks about the solution. The solution being that we can use what is called revegetation or phytoremediation. Now, I introduced this concept because there are three pillars of mining sector sustainability: or the social, the environment, and the economic. Now, the economic sustainability actually tells us that we have to take steps to minimize the negative effect of the mining, and we have to take measures to repair the effect of the mining. That's why you have to do mine land reclamation or remediation. So we need to develop technologies in order to minimize or eliminate the negative impact of mining, which is called concurrent rehabilitation. Then we need to also devise technology to repair the negative effect of mining in order to restore the mine spoil for future use. So we call it post-mining land reclamation. Then we need to use amendment or we can add amendment together with the phytoremediation plant, and that is called assisted phytoremediation. So for instance, over here, I use my different amendment, where I use iron oxide, I use manure, I use nitrogenous fertilizer, then I use biochar at different concentrations at day 1 of the incubation and at day 28 of the incubation. Now the result was that when we got to the area where we have a lot of the treatment with higher concentrations of iron, Fe, what we see over here, F 0.5 means that iron oxide applied at 0.5%. F2 is iron oxide applied at 2%. F5 is iron oxide applied at 5%. 5% of the soil in the jar. So we realize that the arsenic concentration or the solubility or the readily available portion was highly affected by additions of iron oxide. It is because the iron oxide can form what is called both inner sphere and outer sphere complexes. They also have higher surface area, and they are usually carriers of PTEs or arsenic, which is an example. And the same results were found also in the day 8 or the day 28. So both the day 28 and the day 21 realized that the effect of the iron oxide was massive. Iron oxide was able to reduce the readily available portion of the arsenic. So we say that iron oxide rich material can be used to reduce arsenic bioavailability and to mitigate associated human and environmental health risks. Then the other thing you can do is use.
Sorry for cutting you. Just to remind you, you have 5 minutes.
5 minutes?
Yes.
Okay. So the other thing you can do is also to use native plant, which is now the phytoremediation. Now, so in that particular in the book, I have given several different kinds of native plant species like a champion in Ghana, which is called Comolela odorata, like Lantana camara, like Aconia cordifolia, fern, puraria, and all that. So I did this experiment where I collected all these plant species that are growing around the mine. Then when I did the experiment, I realized that the translocation factor, like you can see over here. So we have here Comonella odorata. Here is fern, F. AC is Aconia cordifolia. LC is Lantana camara. PM is Puraria montana. So we can see that the results, the Comonella odorata was able to take up the arsenic into both the shoot and the root. So the pink color is the shoot, then the yellow color is the root. So if the value is above 1, then it means that plant can qualify as a phytoremediation plant for that particular element. So over here we can say that for zinc, Comonella odorata and all the plant species can qualify as phytoremediation plant species for zinc. Then when we come to copper, it is only the Comonella odorata that is able to sequester the toxic element into the shoot, but the rest all were below 1, which means that they may not qualify as appropriate phytoremediation plant for copper. Then for arsenic, none of the plant was able to go above 1, which means that arsenic cannot qualify. Comonella odorata or none of the plant can qualify as a phytoremediation or phytoextraction plant for arsenic. Same would also apply to titanium. Then this is what I was talking about. Here, Comonella odorata can take up arsenic into the shoot, which means that it is phytoextraction plant for arsenic. It can also do same for copper, can do same for titanium, and can do same for zinc. Then we can also introduce species if the native plants are not available. We can use introduce species like ryegrass. Because of my time, I will skip. So now the book is made up of, it's published by the writer on the 19th of May 2025. It is published in English. It's made up of 464 pages. This is the ISBN number, and it weighs 771 grams. It's quite a very big book. It's available online from all major bookshops. If you go to Google, it will give you a whole lot. It's actually making me more popular and making me more relevant to science in our region, not only in our region, but beyond Ghana. So subject disciplines, people in soil science can use it, public health, people in soil biogeochemistry, people in agriculture science, sustainability sciences, environmental sciences. The book is, why did I write the book? It is because Ghana is among the top gold producing countries in the world. And so there are some actions we are taking towards sustainability, and it must be shared with the world so that the world can borrow. There are also challenges that we are facing as a country, which must be shared for other gold producing countries to also borrow. Not only gold producing countries, but even those producing oil and other precious minerals. Then the book also documents native species that can be used to reclaim our mining sites, and it contains practical and on-site case studies. It can be used by senior undergraduate students, graduate students, industry professionals, researchers, and academics. The key selling point, or the uniqueness, or the competitive advantage of the book is that it advances soil size fractionation as a new and uncommon method for identifying soil human health risk in contaminated mining fields. The book provides empirical evidence and scholarship for adoption of revegetation as a viable strategy for remediation of mine-degraded soils. It also provides various case studies in successful application of revegetation towards restoration of former mining sites. It blends hardcore science with laboratory science and with social science, which is very, very, very rare, where a scientific book is talking about both the application of social science and hardcore science to be able to reclaim our mining sites. Then it gives a comprehensive and holistic method for risk assessment with regards to mine land reclamation. These are some of the purchasing platforms you can get it. Then this is the picture of the book. It looks very beautiful when I got the first copy in my hands. Then I've also written other books in the past. Thank you very much for your attention.
Thank you, Dr. Albert, for the interesting presentation, and congratulations on this very beautiful book, as you mentioned, and thanks for sharing it with us, with the community. I pass the floor to Dr. Sam to coordinate the session, and we are happy to receive any questions from our participants. So please feel free to unmute yourself or write your question in the chat. Dr. Sam, would you like to take over the question and answer sessions? Dr. Sam, can you hear me? Okay, not sure if he can hear me. Okay, yes, please unmute yourself. Let's take first question.
Okay. Thank you very much, Crow. I just came back after a longer period of time. Yeah? I really fascinated by the research work and the presentation on the soil pollution and remediation issue. And I appreciate really the extent of the research work, just to detail and very, very informative. Thank you for that. I just, for the sake of triggering discussion, I want to raise some questions. One is mostly we lost the balance between the developmental issue, in this case is mining, and the environmental issue. I am, of course, environmental scientist by training, yeah. But I want to keep the balance between the developmental issue and the environmental issue, especially for the continent Africa. So the balance between the development and the environment is that how much was the arsenic concentration in the soil, for instance? Was it above the permissible limit, so that we can conclude there is arsenic pollution in Ghana? The second concern is the remediation with iron-rich substances. Do you think, Dr. Mensah, do you think this is a sustainable solution? Because mostly when we use iron-rich substance, it is condition dependent. For instance, if the pH of the soil gets changed, the bioavailability of arsenic is also changed. So one time maybe sequestered or can be captured by iron-rich substance, but it can have a potential to be released again, depending on the pH of the soil. So what can you say on this issue? The last point is on the phytoremediation issue. So one of the negative issue pertaining the phytoremediation is the fate of the chemical, or for instance, fate of the arsenic in this case, after accumulated in part of the plant, for instance, be it in the root or in the leaf. So what is the fate of that plant? For instance, if it is grass, it can be consumed by cattle, for instance, and the cattle again, the bioaccumulation and the biomagnification issue, and that is very important. If it is burned, it may be just induced into the human, so that the toxicant concentration level may reach. So what is the fate of arsenic in case of the phytoremediation issue? Thank you very much. I have these three concerns for discussion.
Thank you for the question. Dr. Albert, would you like to address these questions, please?
Yes, please. Thank you so much, Professor, for such an insightful questions. The first thing about the concentrations of the arsenic. Of course, the first thing we do in soil remediation or soil pollution studies, the first thing we do is to do characterization. We do characterization to see if there's a problem, and there's a problem if the element there goes above the threshold. Now, for the arsenic, there was a very big problem, and in fact, in Ghana, arsenic pollution is not only restricted to that particular mining site where I did my work, but it is spread around virtually all the gold mining sites in Ghana. There's a paper that I did where I sort of georeferenced the distribution of arsenic in gold mining hotspots in Ghana, and the results was that there were higher concentrations of arsenic found in the food chain, in the plants, found also in human hair. Some are also found in human blood. Some are found in meat. Others are found in food that people consume. So it's a very widespread issue here in Ghana, and it is because the arsenic is more or less sort of coming from the parent material, which is the arsenopyrite, which is the primary parent material of the gold or the gold mining ore. So the problem with arsenic is very high here in Ghana, and not only in Ghana, but I've also given cases where in Bangladesh there's also very big problem with arsenic, and I also showed also in the map where the map shows us the various countries where arsenic is a major problem. But our problem here in Ghana is that it's connected with gold mining. And the place where I did my work, the arsenic concentration is around 8 grams per kilogram. That is 8,404 milligram per kilogram. And when you convert it to grams, it is 8 grams per kilogram. And this is a disaster, because we are talking about a maximum allowable concentration of 20 to 50 milligram per kilogram. So if you have 8 grams per kilogram, then that's really a disaster. And that's where I captured the picture of the school children swimming in the stagnant water. Then about the sustainability of iron oxide. Of course, iron oxide, there's a very big problem with iron oxide, even though it serves as good option for sort of sequestration of arsenic, and not only arsenic, but also for other toxic elements. But of course, especially when the pH changes is not so much, or when the soil has a higher buffering capacity. Now, it is because the iron can cause something to call, iron oxide can cause something to call secondary pollution effect. The secondary pollution effect is that even though it has sequestered or stabilized the toxic element, it has done so because the environmental conditions are not favorable. When the environmental conditions like pH, like redox conditions, like the dissolved organic carbon or the carbon content, when all those parameters, governing parameters change, the toxic element that has been sequestered or that has been absorbed can also become available. So I agree with you that there's a secondary pollution effect associated with that, because the sequestered element can also be released again when environmental conditions become very favorable and conducive. So what we can do over there is to use combination of options, not to use only the iron oxide as an option, but to blend it with something like maybe with compost, to blend it with other organic amendments like biochar and all that. So when we do that, we'll be able to get a sustainable solution for the secondary pollution effect associated with the use of iron oxide. Then about the fate of the plant, I think one of the ways, there's one chapter in my book, I think chapter 20, where the leading author was talking about how we can dispose of this plants that have sequestered quite a number of heavy metals into their roots or their shoots. And one of the ways that he was proposing is to use what is called incinerator, or to do incineration, or where we can dig a very big hole on the ground and bury those plants in. So when we do that, then that is called incineration. That can help to reduce the effect of the plant becoming nuisance. So that is one of the ways that we can do. Of course, there are other effects, especially when it comes to groundwater pollution, but incineration is one. People also are capable of using it to produce biochar. Others are also using it to produce biochar. So those are some of the ways that we can safely dispose of the toxic element that are sequestered or absorbed by the plant.
Thank you, Dr. Albert, for your answer. We will take another question from Dr. or Mr. Abdullah. Then please, if there is any follow-up question, feel free after that to unmute yourself and answer and ask your question. Yes, please, Dr. Abdullah.
Thank you very much. I'd like to first by congratulating Doctor for a very good presentation. And my question will come in two ways. I don't know, I joined the meeting a little bit late, but at the same time, when you talk about reclaiming spoiled mines, there's the issue of also carbon sequestration. I don't know if that has been taken care of, where different species are planted. Then the other side is on the government aspect. Where I am right now, there is a coal mine, which I visited, and there's issue of reclaiming or revegetation of the spoil mine. Now, at the same time, also within the law here, you find there are legislation with respect to trying to reclaim areas that have been mined over the years through revegetation. But what I find a little bit funny here is this. I don't know whether I want to know that of Ghana experience. Do we have proper monitoring? Because the legislative law that yes, companies that are mining must revegetate or reclaim those land that have been used. But then the aspect of monitoring from part of government to ensure that this law is being followed. Here we have a problem with this. So these are the two observations I want you to really put it. Thank you very much.
Thanks, Dr. Abdullah. Dr. Albert?
So that's a very important issue that has been raised, especially, of course, the first what is it? The first move towards sustainability is political will. That is, it's political will. The will by various governments to make sure that the right thing is being done, and also causing corporations or mining companies to be able to follow the regulations and do what is right. So, for instance, when it comes to, I think there's a chapter in my book where I talk about sustainability in the mineral resource sector, or sustainability in the mining sector. What I did over there was that we saw that various governments, especially in Africa, there's a problem with issues that have to do with sustainability. One, because institutions are not strong. Institutions are sort of, they side with government. So also because of the fact that for political reasons, where government are afraid of losing votes, the right thing is not actually being asked to be done. So I think over here, the main issue is political will. The political will to make sure that the right thing is being done. Now, when it comes to that, there's an agenda. There's a blueprint of operation which we call Agenda 21. And in Agenda 21, it talks about various principles in 27 ways by which we can achieve sustainable development in the 21st century. One of the principles is effective community participation, which is principle number 10, to make sure that people living in mining communities are engaged in mineral decision and mineral resources governance. Then the other thing is also principle number 15, where we make sure that we do the right EIA, the right environmental impact assessment, to make sure that we carry it out with records to the law, and not for any political party. So in short, I think the phytoremediation strategy can be upscaled when there are good institutions, when they're backed by funding and also backed by scientific research. In fact, there's a chapter in the book where the authors of that particular chapter gave a conceptual framework through which you can upscale phytoremediation. And one of the items that were spelled over there is good governance, political will, good institutions, funding. Yeah, so I mean, when it comes to politics, it's very serious, but I think that political will can cause institutions and corporations to do what is right.
Thank you very much, Dr. Albert. Will you please stop sharing your screen, if possible? Can you press the red button, say stop sharing? Yeah, thank you so much. Dr. Abdullah, do you have more questions? I can see your hand still up there, or is it from the old one?
Yes, my question, he did not address the first question, which is to talk about carbon sequestration. Was it also?
Yeah. Sorry, I forgot that. You mean through carbon sequestration through revegetation, right?
Yeah, exactly. Through revegetation, was it taken care of also? Because an aspect of the mining area where species of different plants can be established in order to really get back the quality of the land after mining.
Yeah, of course. Any plant that we may use, at least, especially when we talk about soil amendment like biochar, it was treated under biochar where where it is very recalcitrant, and so biochar can be used to enhance what is called the carbon sequestration. Yeah, so actually what mining companies should do is that they should be able to sort of use some of this what is it options like biochar, and especially when you use biochar and aided revegetation, where we use soil amendment to augment the success of the revegetation. So I think with this, especially trying to promote biochar, we can also achieve the carbon sequestration component of mine site reclamation. Yeah, but there was not a topic that really talked about, let's say, carbon sequestration in reclaimed mining sites. There wasn't a topic like that, but there were snippets of these issues that were mentioned with regards to importance of vegetation, where vegetation can help to capture the carbon from the atmosphere and sink it in the soil, especially with species like trees, with species like Jatropha, other species like Lucina, other species like Acacia. All these species are used in mine reclamation here in Ghana. And by so doing, even though the purpose is not to sequester carbon, but then through that activity of trying to revegetate the land to bring back the fertility and the quality, and to also to decontaminate the area, through all this action with the leaf litter cycling and all that, we can enhance what is called carbon sequestration in these mining areas. Yeah?
No, please give me.
Thank you very much for answering the question. We have another question from Dr. Valentine.
Thank you. Thank you very much. I want to start by appreciating Dr. Kobina for that wonderful initiative. And I must say that this aspect of this book is really very, very timely, because even in Cameroon, we have some mining sites in the east region of the country with a lot of those piles, which the same activities have been carried out. So the effects are felt all around the African continent. I just wanted to find out from Dr. Albert, with regards to the methods used for measuring arsenic and cadmium. I noticed that there were about 7 or 8 methods, and I wanted to find out a little bit concerning the cost of the analysis, because these methods will vary, even including the financial implications. And if, for example, a scientist would like to measure this arsenic in the environment, which of these methods could you recommend as a cost-effective and reliable method? So
I think
please, just a
I'll go
guide.
straight to the question. I'll go straight to the question. But before I answer my question, it's interesting that we are meeting for the first time, Valentine.
Yes,
I'm the Albert guy that we met some time back on.
I remember very well.
You
I
remember?
remember very well. Very
Yeah,
well. That's
it's
why
a very
I'm
small
very
world.
interested. Yes, that's true. Yes.
Yeah, thank you
so
so much.
Mhm.
So when it comes to the cost, I think the easiest way is to use the total element, which is called the total element method, where we use a nitric acid digestion, or we can use aqua regia. That is the basic of all. Of course, it is actually one of the routine measurements that are usually done in labs. So with this one, the first method, which is the total element content, with that method you can estimate the human health risk if you get a very good lab. So that is the basic. Now, the other ones like synchrotron radiation, the other ones like redox chemistry, the other ones like size fractionation, they are very cumbersome, and it requires special special training in those areas to be able to get the actual results. In fact, there's a paper that was written by by some scientists in 2020, and they were calling for Africa to institute what is called Africa photo source, or the beamline. Now, the beamline or the African photo source is more or less like a synchrotron radiation, right? I was in Taiwan, and even in Germany, there's no synchrotron radiation facility. We have to go to Taiwan in order to be able to measure some of these samples, especially when we want to do speciation. It's difficult. It's really difficult, but of course, one way to overcome this is to do more of collaboration with the West or the people in the global North. I think with that collaboration, especially us here in Ghana, in Africa, collaborating with CRO and people in the Netherlands, ISRIC, we'll be able to do more of this sophisticated analysis to be able to get to the root of the problem. Because, mind you, my brother, we cannot identify the problem just by doing the total element method. Because it cannot reveal the actual problem. Either it can overstate the problem or it can understate the problem. You know, so I think with collaboration with people in the North, the scientists on the global the global North, and also with funding coming from organizations like the AU, you know, we can also get some of these African governments to commit to research, where they put some seed money, where scientists can apply to do some of this work, because it is very difficult here in Ghana, especially to be able to get most of the sophisticated analysis that I have outlined. But then I did them because I was in Germany, so I had the opportunity. Okay. So I think with collaboration, we'll be able to do that. Yeah.
Thank you very much.
Yeah, welcome.
Thanks for the question, and thank you for answering all the questions, Dr. Albert. Thank you very much for sharing your book with us, with the CoP member. And before I close the showcase today, I will ask if there's anybody there's no messages in the chat, but if anybody want to ask a final question, please feel free. Otherwise, we just close the showcase here.
It's not a question, just a commendation.
Yes, I pass you the floor to close it, please. Thank you.
Yeah, thank you very much. Thank you, Dr. Mensah, for the good presentation and for your willingness to showcase what you have been doing in Ghana. That's a wonderful work, and the presentation was clear. Thanks for the knowledge sharing.
Thank you so much for the opportunity.
Thanks a lot for all our guests for making time to attend our showcase. Thank you, Dr. Sam, also for leading this, and for Dr. Albert once again for sharing your book with us. Thank you all, and wish you all a lovely afternoon or evening where you are. Thank you so much. Bye-bye.
Thank you so much. Thank you, everybody.